With the pineal gland, we're heading back up to the brain. Now the pineal gland, if you remember back from the nervous system, the pineal gland was part of the diencephalon. It was on the posterior side. This is the pineal gland right here. It's found just on the posterior aspect of the internal part of the brain. The pineal gland is going to contain pinealocytes. Those are the cells that produce melatonin. Now, melatonin, not melanin, but melatonin is derived from serotonin. So this melatonin, we have to be careful not to mix it up with melanin, melatonin. So what does melatonin do? Melatonin can help with timing of sexual maturation and the timing of puberty. It also, and probably the one people recognize the most for, is melatonin is dealing with day-night cycles. So if you're normal awake during the day, asleep at night, or maybe you're asleep during the day and awake at night. But whatever your cycle is, whatever your natural rhythm is of sleep versus waking up, that is partly in play because of melatonin. But melatonin also deals with other cycles, other parts that are going in a roundabout fashion. You have body temperature, sleep, appetite. They all have their own rhythms to them. Think about body temperature. Well, you have different periods where you're warmer and colder throughout the day. As you slow down for sleep, your body cools down. As you really get moving through the day, the body warms up. If you're dealing with sleep, sure, day-night sleep usually corresponds. Looking at appetite. Well, depending on how you've kind of trained your body, maybe it's hungry in the morning at breakfast. Then it gets hungry for lunch, hungry for dinner. Or maybe you only do 2 meals in a day, so you're hungry at breakfast time, and then you're not really hungry again until dinner time. Or whatever other patterns you have. Maybe it's more of a snacking. You snack 6 times a day instead of meals. Whatever your body's gotten used to, it gets this rhythm, this kind of cadence to it, where it's used to what's going on at a certain time. That's the pineal gland. Next up is the pancreas. Now the pancreas is unique because the pancreas is both exocrine and endocrine. What I mean by that is, exocrine, we'll look at these acinar cells. Now the acinar cells are producing digestive enzymes. So this is not endocrine. This is the exocrine. We're producing the digestive enzymes. But now flipping to the endocrine side, you have these pancreatic islets, also known as the islets of Langerhans. But the pancreatic islets are what produce the hormones. Now, these are the endocrine cells. While a majority of the pancreas are acinar cells, these little tiny areas, these pancreatic islets, are the endocrine aspect. So inside the pancreatic islets, you're going to have 3 different cell types. We're only looking at 2 though. We have the alpha cells and the beta cells. Now the alpha cells are producing glucagon. If you think about the name glucagon, glucose is gone. So glucagon is going to be a hyperglycemic hormone. That means it's meant to raise your blood sugar. While the beta cells produce insulin. Now, insulin is a hypoglycemic hormone. That means insulin helps to reduce your blood sugar levels. So glucagon, insulin, completely antagonistic hormones, both produced by the pancreatic islets. Alpha cells, glucagon, beta cells, insulin. You kind of think of the alpha cells are ahead of the beta cells because A comes before B, glucagon before insulin, G before I, or however you want to remember it. But alpha cells, glucagon, beta cells, insulin. So look at the image here. You can notice the pancreas itself. Everything in green, these glands right here, that's all going to be exocrine. That's going for digestion. What we're focusing on are these little blue patches. The little blue patches are the pancreatic islets. Now, you do not need to worry about which is an alpha or which is a beta cell in this image. They're labeled, sure, but you don't have to worry about which is which. Just know that both alpha and beta cells are inside the pancreatic islets. Alpha produces glucagon, Beta cells produce insulin. So let's look at glucagon a little bit more. Glucagon itself is really targeting the liver. That's the main thing. Because in the liver, it's going to promote glycogenolysis. Now, in the case of glycogenolysis, you're breaking down glycogen into glucose. Well, glycogen is literally just a string of glucose molecules. The liver stores glycogen. So glycogenolysis is taking your stored glucose and basically pulling it back out and putting glucose in the blood. It's a way of getting energy into the system. It's a way of making sure you maintain that homeostatic level of glucose in the blood. So glucagon is being secreted when you're in between meals, overnight, times that you have to bring your blood glucose back up because you haven't been eating. But it also can deal with gluconeogenesis. Now, in gluconeogenesis, you'll still get glucose, but now you're using non-carbohydrate sources. Think lipids, proteins. So it's not the ideal, but it can function. The whole goal, though, is release glucose into the blood. Glucagon, glucose is gone, so releasing it into the blood. Glucagon. The other side, the flip side of the coin, is insulin. Now, insulin is going to lower blood glucose levels. The idea is you've just eaten something. Your glucose levels went up. Insulin will lower those glucose levels. You can lower those glucose levels, lower the blood glucose levels by enhancing membrane transport. Allowing glucose to travel across the membrane easier gets the glucose out of the blood. So it's making sure that glucose goes into fat cells, goes into muscle cells, so it can be stored for later use. But insulin also has an interesting role in dealing with neural development, learning, memory. So it also is aiding the nervous system overall here. So sure, it's important for glucose levels, but it's also important in your learning abilities and your memory control. So kind of think back to that nervous system. This actually plays a part in there. And it's meant to inhibit glucogenolysis and gluconeogenesis. Basically, you're trying to prevent the formation of new glucose molecules. Insulin wants to keep the units stored. Keep it as glycogen in the liver. Keep it as lipids. Keep it as proteins. Do not convert all those sources into glucose. So when we're looking at this, kind of an idea here. I'm going to throw this up full screen for a second. If you lose the balance of glucose, which means you're not maintaining that roughly 90 milligram per 100 mils of blood. So your blood glucose levels have increased. Which hormone we're dealing with? Which glands? Well, start with the pancreas. And the pancreas should secrete what if we're trying to bring glucose back down? Well, you better secrete insulin. Insulin is going to help to lower your blood glucose levels. It does that by going to the cells and saying, hey, take up more glucose. Make sure you absorb glucose. Get it out of the blood. As well as going to the liver and saying, hey, pick up more glucose. Take that glucose, convert to glycogen, and store it. We don't want it in the bloodstream. That ends up lowering your blood glucose levels, and therefore you're back to your normal homeostatic levels. Or the flip side, your blood glucose levels fall. Again, you still stimulate the pancreas, but which hormone would help you to increase blood glucose levels? Yeah, glucagon. So glucagon can help to increase blood glucose levels because it can stimulate the breakdown of glycogen to glucose from the liver. So all that glycogen that was stored, simply start breaking it down, releasing glucose into the blood. That increases blood glucose levels, and therefore you're back to homeostatic balance. The idea is it's a constant balancing act, kind of like a seesaw. Throughout the day, you eat food, gotta bring that blood glucose down. Then you don't eat for a while. You got to bring that blood glucose up. Then you eat again, bring it back down. Don't eat for a while, bring it back up. So your body's always trying to balance these two out. What you don't want to do, though, is have both insulin and glucagon secreted at the same time. They're antagonistic hormones. So you want one or the other, but you don't want both at the same time. So looking at the pineal gland, looking at the pancreas, the idea is moving through the endocrine glands of the body.